So yeah, Vivien Parmentier. I'll start by making this work. Good. Yes. Presenting me a bit. I'm one of those lucky kids that actually developed some passion for astronomy. A while ago as a kid, looking at Saturn through a telescope. I'm sure a lot of you have this feeling. And I was lucky enough to be good at school, so I did my undergrad in Paris and then managed to start a PhD in astrophysics. Here in Nice, by the sea, beautiful city, I recommend it. Then academics being academics, you usually have to move around the world, so I had to do a postdoc in Santa Cruz, by the sea again, as you are not complaining. Arizona, so that's a lot of cacti. Back in France, in Marseille, and finally landed in Oxford as a professor last year. So, pretty nice dream became reality. And in the meantime, got married and 2 kids. Life is good. Anyway. So you've heard about me now, and we're gonna hear a bit about exoplanets. So first exoplanet was discovered a while ago by some people next door, actually. And this is a small movie showing the galaxy here. This is galactic center, the spiral arms. This is the sun, as we're here. And I'm going to show in this movie point the stars where we found planets one by one as a function of here. So you can give a small insight of from where we come and where we're going. So remember, we started with the sun and the 8 planets around the sun. And don't care about that, we'll deal with that later. But you'll see here some points. So this is just a zoom-in version, right? We start thinking of those guys, and this number increases. And there's some weird pattern here, and that's where we are, right? So those are all the stars around which we found another planet, a planet that's not in the solar system. There's a few things to see here. First, this is roughly our neighborhood. We haven't found stuff around there. And then you see this weird spikes, like this thing is using a fun technique which is called microlensing, where you need to be really precise and have a star going in front of the star that has the planet. And then you have some magic, general relativity thing that bends the light. And you can see a planet. That's why you see them around the galactic center, because there's a lot of stars here. So the probability to have 2 star lining is good. Anyway, so that's where the planets are. And yeah, we know roughly, let's say, 4,000 planets now. And we've been able to do statistics, and you can say that basically around what we've learned is that it's easy for a star to make a planet. Like around mainly, literally, every star around there in the sky, it's very likely there's a planet around there. Okay. People might wonder, why do we want to study exoplanets? And it's not, it's a question that dates back to at least 1584 by Giovanni Bruno, that had a bit of bad luck in his life at the end and got burned by the church. So they excused themselves like a century ago. So it's better now, but. And he was actually saying, one of the reasons the church was upset with him is that he was saying the universe is infinite, it has no center, we're not the center of the universe, and by the way, there's planets out there, and there's probably life everywhere in the galaxy. But we're nothing special. Do we want to find them so we can have a new holiday place, go to TripAdvisor and buy your shutter. Next one's leaving for Proxima Rabi. Proxima Centauri B, with the best spacecraft we can do now is 90,000 years. For the closest exoplanets. Probably no. So really, the big questions we try to answer is that. One of them is, how unique are we? How unique is the solar system? How lucky are we to have a solar system the way it is? And obviously, are we alone? You know, either some other living creatures around there in the universe big. But the really fun thing that's happening is that we have no idea, really, how life actually formed on Earth. Like, you can ask biologists, etc. They don't know how this whole thing started. And still, like a big, big research. And something we don't know is, if all the conditions are right, what's the probability that life actually starts? Right? And if there's 1 million planets out there, but the probability is 1 over 1 million, then we're the only ones. So, you know, you're dealing with big numbers both sides, and actually looking out there, see if we see, life around there is probably, astronomy can probably try to answer this question. Maybe faster than biologists, I'm not sure. We'll see. Where's the race? Anyway, so how do we find these exoplanets? So to find exoplanets, the first techniques that was used is by using the most precise science that we have now, which is spectroscopy. We're really good about knowing, so this is a spectrum of the sun. Okay, so take this, this is a rainbow basically. Take the sun and spread the light. It goes from red to blue, rainbow. And you can see that there's a lot of places where there's no light. Okay? And all those places you can zoom in, in this portion, and those are all lines, absorption lines by atoms that are on the sun. And so we know really well by both calculation and both experiments that, iron actually absorbs a lot into these exact wavelengths, and then nickel absorbs a lot into these wavelengths, etc., etc. So we know this position of the lines really well. And we're going to use to detect planets a very fun effect, which is the Doppler effect. I'm sure a lot of you might have heard, a lot of you might have not. It's basically, you're sitting at home and suddenly you hear like a police car passing by, and not sure you cannot do that anymore. But usually when you hear it, it's like right? Like when the car comes to you, the sound gets more pitchy, and then when it goes further away, it gets more. How do you say gray? You say gray? More low frequency. Okay, good. More low frequency. Same thing happens with light. If something moves towards me, it's going to be bluer. Bluer is like higher frequency. If somebody moves away from me, it's going to be redder. Okay? So objects change colors when they move compared to me. You have to move, you have to be quite precise to know it. If you walk towards me, you're not seeing me bluer now, but with good instruments, you could. And so what we're going to use is the fact that when you have a star on a planet, it's not actually the planet orbiting around the star, it's both of them orbiting around what we call the center of mass. Okay? So a planet, if there's a planet orbiting a star, it means that the star is moving too. And the star emits a lot of light. And we can look at the spectral lines of the star here, okay, and compare them to what we have in the lab. And when the star goes closer to us, all those lines get shifted towards the blue, and when the star is moving away from us, shifted toward the red. Okay? So we compare, that's what's actually done, we compare the position of those stuff with what we have on the map. And we see there's a periodic variation. Okay? And that's the observation for the first exoplanet ever discovered. Okay? This is actually what you're showing here is the velocity, so you can translate that into stellar velocity basically. This is the velocity of the star, okay, those points, as a function of time. For four different epochs. You can see, it's decreasing, increasing, increasing, decreasing, increasing, etc., etc. You can pile all this together by saying it's periodic, and you get this very nice thing. Right. So here, first exoplanet. That's the real stuff. So what can you learn from that? You've seen it's a planet. What can you learn from that? Two things. First, you can see the period. 4 days. This is a planet orbiting 4 days around its star. Every 4 days is a year for this planet, basically. The second thing you can see is that the mass is 4.5 times the mass of Jupiter. Okay? This is a very big planet orbiting very close to the star. To go around in 4 days, you really need to be close, because you can't be that fast, right? You need to be really close to the star, so you can actually go around very fast. And I'm sure some of you know that was actually discovered by Michel Mayor and Didier Queloz, who has an office next door, and they got the Nobel Prize this year. Good for them. Nice medal and nice money. But the question you can ask is, yeah, sure, I mean, we know there's planet out there. Why would you give a Nobel Prize to somebody who discovers a planet? What's the big deal? And there was a big deal here. The first thing is that sorry. Whoop. Good. Okay. Okay, so Cambridge, right? You all know this view. I'm not sure where this was. I didn't think that, but I'm sure a lot of you know that. Nice sunset in Cambridge. And now I'm going to pretend that I'm moving towards this first exoplanet. It's called 51 Peg. 51 Peg SEV. Let's move the Earth as close to its star than 51 Peg is close to its star. And you know, that's what your sunset looks like. The sun would be like 35, 40 degrees in the sky. That's a pretty big sun. Let's move that back fast, because we'll get burned very fast if we do that. But so yeah, I was saying, what's the big deal? It's a big deal because nobody, well, one person, actually here too, John Papaloisu and Doug Lane, but with Santa Cruz. Apart from them, nobody was thinking you could have such a planet. So why is that? Solar system, right? And what do you have in the solar system? The first 4 planets, small rocks. The 4 planets that are out there, big gas, giants, right? So every single formation model we had at the time was tuned from rocky planets close in and gas giants further away. That was the only point we had. So sure, everybody was like, surely, if you observe exoplanets, then it's going to be like rocky stuff close in and gas giants further. And we had really good arguments, which is that when you form planets, you form them in a disk. This part of the disk is much hotter because it's closer to the star. If it's hotter, you don't have snow, you don't have ice, right? Or the ice is evaporated. If you don't have ice, the small grains, they don't have to stick together, right? It's like rocks bonding, and it's not super sticky. Whereas if you're further away, right, all the water is condensed into ice, then it's much easier to form big balls and to form big planets. All works out. And obviously, the first planet we find is this, right? It doesn't fit the thing. So they serve something for 2 reasons. The first is that they had the guts to look for something that nobody was thinking would be there. So this is very nice. And then it's really changed our view. Because now you have to explain this. Okay? Planet formation model, suddenly they were like, oh, we are wrong. Right? Everything we were thinking is completely wrong. And so then came this idea that planets form actually in the disk. So imagine this is the sun, this is the disk in which planet forms, and you form a big Jupiter, a nice few rocky planets, Perseus among them. And when you put a planet in the disk, the planet tries to rotate at the speed that physics tells him, which is the Keplerian speed. Like this guy Johannes Kepler calculated that, where you go. But the disk, him, doesn't like to go at this speed. He likes to go a bit slower. And so there's like a drag, a wind. It's like the planet is feeling a wind when it's trying to orbit. And doesn't like that. That slows it down. If it slows it down, it's going to move it downward. And so what we expect is that happens, is that whoop, and that could have been our fate. Right? So how do you form a hot Jupiter? We could lose a hot Jupiter. You just form a Jupiter's gas. A gas giant planet in the disk, and it naturally is going to migrate toward the border of the disk. Okay? And in the process, it's going to wipe out every single rocky planet that you can have here. So, sure. So now, it's good. We found a hot Jupiter, and we have a new model that explains it. But obviously it raises the question, what happens in our case? Right? We're from Jupiter, and I'm still talking to you. So, that cannot be right. And so here came a really nice idea that requires a bit of fine-tuning, but not as much as you're seeing, which is that we have two planets, two gas-giant planets, Jupiter, Saturn. We have the other two, but they're not as important. So we have Jupiter, Saturn. So what we think has happened is that Jupiter, yes, starts migrating, like this, pushes everybody, but then Saturn grows and migrates back. Okay? Gets to Jupiter, they get into what's called a resonance, meaning that this one orbits twice as fast as this one. And there's a very funny, weird effect that happens, is that Saturn is basically saying, hey, Jupiter, you know, come see, there's something I want to show you. Brings him back there. Saying like, you know, there's like some humans that want to live one day in this planet. Let's keep it that way. And so in a way, we're really unique because we had, you know, this kind of special interaction in the solar system that involved our two gas giant planets. So, so yeah, that's really, the discovery of future unpeg really changed all our view of planet formation. Well, there's more, but I'll switch to something else a bit now. We can talk about that later during the break if you want. So what I really do for my living is more dealing with the atmospheres of these guys. Okay? Because not only now we know a lot of planets, but we can actually peer through their atmosphere and try to know what's inside their atmosphere, which I find pretty impressive. So those are all the planets we know. Okay? All the gray dots. That's like the higher, the bigger. It's the radius. And that's their period, how fast they go around their star, so it's kind of the distance too. And so the first thing you can see is that we have found nothing like the solar system for now. The main reason is that we're not able to do that. It's all. We're able to find big planets close to their star, because that's more easy, but we're not able to find Earth's planets at Earth's distance from their star. That's rare. And yeah, so we can't detect those ones. And the color points I have here are all the planets for which we have some information about their atmosphere. Okay? But there's a lot of them. We'll start being able to say a lot of things about a lot of atmosphere of a lot of planets. But mainly are Jupiters. Right? That's the second thing why we like them. They're like the easiest planet ever to study compared to all the others. If they didn't exist, I could have earned my salary. So I'm happy they're here. We're starting to go towards stuff that would be like warmer version of Neptune, and even like hot super Earths, like planets that are so hot, rocky but so hot they might have lava oceans on the surface. So one fun thing that happens with these planets, because you know most of them are close in, and so one fun thing that can happen is what's called tidal looking. Do you recognize the moon here? Is that how it looks like in the sky usually? All right, so this is the far side of the moon, the side we never see. And the reason of that is that the moon is always showing the same face to the Earth. And that's the equilibrium when you put two bodies together that rotate. That's how they like to be. They like to face each other. If you wait a really long time, the moon were a bit bigger, Earth would actually be always facing the same face to the moon, and you would only see the moon from England, but not from the US. Different perspective. So anyway, you can, you know, make up physics and calculate some time scale. And what we expect is that all those guys are going to be in that state with a star. So all those hot Jupiter, they're going to be big ball of gas, always facing the star with the same face. Okay? So, good. We have planets. I told you we know about the atmospheres. How do we do that? No, doesn't seem that easy. Can we go there? Not really. So again, that's astronomy. We have to rely on some tricks. The trick here is to wait for the planet to go in front of the star. That's actually a very good way to find planets. We just point the telescope, look at the star, and each time there's some dimming, it's like, oh, planets. So if we do that, that's what we observe, right? Star brightness, and then the planet goes in front, so brightness goes down, then it goes back to normal. Easy. But what you can do is try to look at that with different colors. Okay? Imagine I go here. This is actually Earth. okay? An image from a satellite, Imawari. And that's the moon. It's a satellite used to, it's a weather forecast thing. So normally it looks down. But sometimes, you know, they like to fool around, so they turn it a bit and to look at the moon rising at the rim of the Earth. And that's at AOPP. Actually, in Oxford, actually don't know those data, do science with them. But when I saw that, I asked this guy standing in front, oh, no, this is nice. This is like what we do in exoplanets. Do you have that in multiple colors? He's like, yeah, sure. So you can look at the color, 8.6 micron, where there's not much absorption in the atmosphere. And you can look, right? The Earth looks this side. And you can keep the moon here, that's overexposed, as a reference, right? Then, now I'm going to look in the color where ozone, O3, is actually a good absorber and emitter. And that's what the picture looks like, right? I'm going to flick between the two, right? So in one case, here, right? Inside the O3 band, the Earth appears bigger. Okay? That's because ozone is here in the atmosphere and actually emits light. And when it emits light, it actually absorbs light too, so it really looks bigger if you put it in front of the star. And that's what we're using. What we're doing is, if I come back to you, here, we're looking at the side, this brightness dip at different colors. Colors where water absorbs, colors where water doesn't absorb. We see the size of the planet changing with color, basically. And in a way, you know, that's what you can witness during lunar eclipse. This is basically the exact same thing. Why is a lunar eclipse red? That's because the Earth's ray lights have been filtered through the atmosphere, and only the red ones have been able to reach the moon. It's a bit similar. So anyway, back to science. So what we try to get is here, that's size of the planet, okay, here. The higher, the bigger the planet looks like, as a function of color, so wavelengths. That's optical data, that's like blue, and that's like red. And so that's where the expectation for those kind of planets. Okay, we were expecting, by doing this experiment, to have very nice variation here, and this is sodium absorption, okay? And very big absorption here by potassium, and then there's water, and more water afterwards. Okay, great, prediction. Now, science. Let's take a telescope and look at this thing. Bam! Oops. Oops. Doesn't go through that, right? Why? No, it doesn't go through that. So that's the real observation we get. And yeah, that's all the same. Pretty fun. Which means something is going on. What we think is going on is that you get clouds. Clouds at the limb of the planet that are blocking the view. And so they're blocking all this, and they make what clouds know what to make is ray scattering, which is just basically here, like flattish slope, downward slope. Okay? But if you look precisely enough, you can see the sodium here that peeks through the clouds. Love this observation. Okay? So here we're saying clouds and sodium absorption above the clouds. So this planet has sodium, gaseous sodium. You don't often encounter gaseous sodium on Earth. That's because it's solid on Earth, you know, NaCl, you put it on your plate and you eat it, it's in the body. Here, it's so hot, your temperatures around, you know, 1,000, 2,000 degrees, that every mineral is basically, like sodium, is basically vaporized, and so we can see the sodium, okay? So, now we have a problem, because, right, we have sodium here, and we'd like to know how much sodium there are. Because how much sodium there are in the atmosphere, and we can tie that to where the planet formed. Did the planet form in the part where sodium was gaseous or not? Did it form close? Did it form far? Did it form far and move close? Or did it form close and just stay there? There's a lot of questions about how these things form. But the only thing we can measure is this ratio between the sodium abundance and the cloud abundance, and we have no idea what the cloud abundance. We're kind of stuck. Okay? We'd love to know what the clouds are made of. That's a nice cartoon drawing of somebody falling in the atmosphere of Jupiter. And Jupiter is nice because you have this beautiful ammonia cloud, then well, ammonia gas, and ammonia hydrosulfide clouds, and there's water clouds below, and then that's like the deep dark places. You don't want to know what's happening there. Okay. So you could say easy, if I know what a cloud is, I know at which place it is, but again, we don't know what they're made. So now if we go back a bit closer to home, if you look around in the sky, every single body that has an atmosphere that we found have clouds. Right? Every single planet and moon in the solar system that have an atmosphere, reasonably something that's an atmosphere has clouds. Venus, obviously, Earth, Mars has tons of water and CO2 clouds. Uranus has CH4 clouds. Jupiter has clouds. Neptune has clouds. That's Saturn, I guess. Titan's full of many A's, but it's still like clouds. And even Pluto. Pluto, I think this is like a nice Pluto cloud. And then it has haze layers. Okay? So we have a huge diversity of clouds. Every planet is able to make clouds, even if their conditions is very different. They just make clouds from different stuff. Okay? And so I'm back here with my planet. So again, this is again the radius of the planet. The bigger, the higher I am, the bigger the planet. And this is now the temperature of the planet. Okay? The more redder, the more hot is the planet. And so hot Jupiter is here. And so we know, right? Earth is here. We make H2O clouds on Earth, no problem. And we know that if you go to Mars, you get clouds of carbon dioxide. And if you go to Jupiter, NH3, if you go to Titan, CH4. Okay. Now, Venus, H2SO. Now imagine that's an image of Titan from the Huygens lander running on Titan. And imagine you live on Titan, and those look like very nice rocks, but they're actually not rocks. They're what you would think are rocks when you're in Titan. Those are actually ice cubes. Okay, water ice cubes, this big stuff. So when you're in Titan, right, rocks are ice cubes. So imagine you live in Titan, and somebody you take a small holiday to Earth, and you go to the Grand Canyon, and you'd be like, oh my God, flowing rocks in the atmosphere, amazing. Right. So now we can extrapolate. Imagine you're on Earth and you want to travel to 51 peg. Well, then rocks, if you warm it up, it turns into lava. And you push the lava into the atmosphere, it turns into droplet. That's clouds for you. And so what we expect the clouds to be made of on those guys are those weird minerals, which are silicates. This is basically sand, grains of sands, okay? Corundum, which is basically what is in ruby, the gemstone. So, yeah, pretty fun stuff. So, okay, nice prediction. We shouldn't have been that much surprised that there were clouds there. Can we know more about those clouds by looking at them? So, I'm going to show you now another way to look at this planet. That's pretty cool. So we know the planets are tidal, right? So we know the geometry. We know when we see the day side. We know when we see the night side. That's just geometry. What I'm going to show you here is, as a function of time, how bright the whole star plus planet system is. When you look with this guy, which is the Hubble Space Telescope. So we're looking infrared light. Infrared light, we all emit infrared light. If you are, like those special boogers that allow you to see in the dark, that's looking at infrared light from you. And so the hotter you are, the more you emit infrared light. So what we're going to see is basically the total light emitted by those two guys as a function of time. Okay. So here we go. Then it goes around, right? I'm here. And as the planet turns around, I start seeing the day side of the planet. This is a temperature map, right? Start seeing the day side. Then I start seeing more and more light. Then planet disappears, bloop, just see the star. Then back, and then I'm now going to see the night side. It gets cooler, gets dimmer. Okay. So that's our second fancy trick. And here, it goes in front of the star. Bloop, that's a transit. It's actually going down there. So it's pretty big. So you need to be really precise to see that. Okay, this is really small signal. That's why we need to go to space. And so from that thing, this is again a real observation, we can learn two things, usually. Right? The size of this thing is basically directly related to how hot is the day side, how cold is the night side. Right? The hotter the day side, the higher this is going to be. The colder the night side, the smaller this is going to be. Okay? And the second thing you can see here that's pretty fun is that, right, the maximum is not here. It's not when we should see the full day side. It's like a bit shifted. And this is telling you that the hottest point of the planet is not exactly at the substellar point. Right? It's hotter at 2 o'clock than noon, basically. Yeah? That makes sense? It makes sense on Earth because, right, you're on Earth warms up, then turns a bit, and keeps warming up. And so it's actually a bit hotter afternoon. But here, you're not doing that, right? The planet's just spinning around, so it should be hotter at noon. And so what we're saying is happening here is that instead of the planet rotating, you have big winds that are trying to carry all the energy they receive on the day side to the night side. Okay? And that's actually what makes the temperature not symmetric in the planet. So how do we try to understand a bit that? That's actually my job. So I take models. So I split the planet into small cubes like this. Then I take equations that people derive for me. I'm not that smart. And then I ask a big computer to solve this equation into those cubes and just integrate over and over and over. Okay? And that's what I get. So this is temperature map for a similar planet that we've just seen. So imagine if that were Earth, right? This would be the UK, Africa, United States, Australia, just random map. But now, right, the substellar point is here, and you can see all the arrows are the winds that are carrying stuff around to the east, right? And I'm actually reasonably predicting the day-night contrast on the hotspot shape. So the second thing pretty fun is that we've done that for thermal radiation, right? Which tells you about temperature. We have another spacecraft out there that's named Kepler. And Kepler has been able to look at optical light, which is reflected light. And if there's one thing we know clouds do, it's reflecting the light. So with that, we can actually make a cloud map with the same style. And that's a cloud map for this planet. And what you can see that's really fun is that they're anti-correlated. Right? There's clouds on the west and not on the east, whereas it's hot on the east and not on the west. Okay? So clouds form where it's cold and disappear where it's hot. That makes sense? Fun. And that's roughly what this is predicting. Right? So usually this would be a condensation curve, so we'd expect to have clouds all here. That's the day side, and not here. And to tell you, this is really different than clouds on Earth. It's a really different way of thinking with clouds. So how do you form clouds on Earth? Right? You take wet, moist air here and just shoot it upward. Right? When you see that in summer, there's an updraft here and a downdraft here. And that's why you have a cloud forming. And that's what roughly explains cloudiness on Earth. This is, I love this map. This map is a map of pure cloudiness on Earth. There's no continents drawn here. But you still see them because clouds don't behave the same way in continents and in land. But you don't see the UK because clouds don't really behave here. And what you see here is that at the equator there's a lot of cloud. That's because there's an upwelling at the equator, and in the deserts there's not a lot of clouds. That's because you have upwelling, the same thing. And so here, cloud formation is radically different in the sense that to form cloud, you need to bring the stuff from the day side towards the night side where it's cooler to actually form cloud. So, in the last minute, I'm going to take you in a small spaceship. We'll try to travel to one of those planets I just modeled. A few of those planets I just modeled. Whoop. And that's the fun of this job, is that, right, you can do science, but you can also ask the models what would it look like if I were looking at it. But just converting the flux I get as what a human body would be seeing. What you're saying is this would be a picture you would be seeing. This is ray scattering, very dark blue because of sodium absorption that absorbs all the red. this is the clouds reflecting light. And this is the planet that's so hot that it's actually glowing like charcoal on the hottest point. And the fun stuff is that different clouds will give you different colors. You could make clouds made of salts, Na2S, very, very wide, and you can get those like orangish clouds of MNS, you know, those A2O3. All those planets are different planets. And for the story, yeah, those guys are actually what's in gemstones. You know, it actually rains gemstones in the planets. And I leave you with this good weather forecast.